is continuing to perform research on the effectiveness of his PAR intervention and following students' persistence and communication skills in greater detail. It's even recently been adapted into a physics context with some positive results. And so just to show you a little bit, here's some quotes from some preliminary results of Dan's research on persistence. So these persistence skills are particularly important as students often start off college with a somewhat skewed perspective on how long math and science problems should take. So there's been some research where researchers have talked to hundreds of high school students about how long they expect math problems should take. And for the question, how long should it take to solve a typical math homework problem, the average answer was actually under 2 minutes. Researchers also asked an additional question, what's a reasonable amount of time to work on a problem before you know it's impossible? The highest answer was only 20 minutes, with the average being much less than that. And students would say things like, normal problems should only take me 30 seconds to 2 minutes, where actually if I know I should give up if it takes much more than 5. So students actually had their perception of how long math problems should take was pretty short. Managing student expectations, particularly in introductory courses, and also supporting their persistence skills is a big part of what open-ended and rich problems can support. So if we really want to emphasize higher order STEM skills, where do we get our problems? Well, one possibility is to adapt traditional textbook problems to better align with our learning goals. So now Stephanie Chastain will tell us a little bit about a concerted effort to adapt upper division physics textbook problems.
So homework is a really important part of student learning, but oftentimes the homework in the textbook is really focused on calculation or simple recall and doesn't get at some of your higher learning goals. So this was the case in a course we were involved with, a junior level course in electricity and magnetism, and we had a lot of learning goals that really went beyond traditional sort of simple calculation. We wanted students to use common physics tools like approximations. We wanted them to visualize the parameters of the problem, to make sense of their answer, and to connect their answer to a real world context. But this wasn't always present in the traditional problems. So this is a problem from Griffith's electricity and magnetism text. If you're not in physics, it will look complicated, but it's actually a somewhat plug and chug kind of problem. It takes some understanding of the physics, but once you know how to go about it, you can go ahead and calculate it and not get a whole lot of insight into the problem.
Here we see how this calculational question was adapted. In blue are the additions that they made, and I'm just going to point out 2 pieces here. First, that they ask students to actually sketch a function in a way that clearly describes its characteristics. It's really important. And second, they ask students to verify their result using a different problem-solving method.
A lot of the things we did in this problem and other problems in this course are things that you can do, I think, to a lot of traditional homework problems. So we gave a real-world context, but you could also ask students when might a problem like this arise. You could ask them for the real-world context. We asked students to sketch something. You could also ask students for other visual representations like graphs. And ask them to explain or discuss what it is that they're finding. So this really indicates that you value that process. And then you can ask students to engage in good problem-solving practices. This is something that we did a lot because it was really important for us, like checking that their answer is consistent or that it made physical sense, checking their units, looking at the origin, listing their assumptions. Those are all sorts of things that we really wanted to make clear should be part of their standard problem-solving practice. And then finally, we might note some interesting aspects of the problem. So these were all aimed at having students make more sense of the calculations that they were doing, and I think are applicable in a lot of courses.
So our last example is going to be from Colleen Lewis, a computer science faculty member at Harvey Mudd. And another way of adapting traditional assignments to be a little more open-ended is to ask students to take an idea they've been practicing and apply it into a new context that they're interested in studying. And so Colleen's going to tell us a little bit about how she does that.
So a lot of the assignments at Harvey Mudd in the intro computer science course allow the opportunity to use the tools that were required to be practiced on the assignment to go further. You had to do this, but you can use these same tools to do all these amazing things. And I think providing those opportunities allows students to see value in the assignment because it aligns with their own interests, to feel powerful in what they can accomplish with those new tools. And that it's not just about some external evaluation of the performance on that task, but they might use these tools in creative ways to extend what they've already accomplished in the homework assignment. And I think by being encouraged to extend the homework assignment, it really provides the opportunity to reframe homework as an opportunity to build a set of tools that you can do then cool things with.
I asked Colleen if she could share with us an example from her course, so now take a look at this slide. And this is the very first introductory computer science course assignment she gives, where her students are exploring the Racket programming language and looking at some basic functions for creating graphics. And the final problem on this homework set is an extra credit problem where students can extend their practice with these basic functions to create an image of their choosing. So I thought this was an interesting approach because we often want students to apply ideas they've learned to a new context. And in this case, students get to actually pick the new context as one that they particularly care about. In this video, we've seen lots of different approaches to supporting students in higher order STEM skills through open-ended rich problems. So we've seen the value of students seeing one another's work, and also ways of helping students really close that feedback loop to iterate on and improve their learning.